Hey guys, I'm going to talk about Fubini's theorem for general regions, how to find the volume enclosed between the three-dimensional surface defined by the function of x and t and the z equals 0 plane. So some of the elements that you see in the formula here are explained over here, but I'll go over it. So I'm going to consider this one here, the situation. So the lower bounding function is going to describe the lower value of t at each value of x for all x contained in the region that you're trying to describe on the xt plane. And c1 of x is going to describe the upper bounding value of t for each value of x. A and B are going to describe the lower and upper bounds of x respectively. And so what you're going to get is something that looks like this. So you're going to have a upper bounding function, a lower bounding function. You're going to define that. Then you're going to define the area across. So that's going to define the bounds of t. And then you're going to define constant bounds for x. In this case, you could only do it like this, because if you were trying to do it like this, you'd be assuming that there is continuity from here to here over the region. But you can see there's sort of a lump, which means you'd be accounting for area in that region which is not actually there. So in this case, you can only do this. Pretty nice situation that comes up when there's a parametric equation relating the values of x and t along the perimeter. So what that means is that you could solve for x or t just using that one equation. So what that means really is that h of t is going to be the inverse function of c of x. So the bounding functions are each other's inverse. And you can also use both these methods to integrate over that region, some function over that region. So taking a double integral can still be thought of as a Riemann sum. So it's the three-dimensional case, whereas the two-dimensional case would be the sum of infinitely many rectangles of base width dx and height f of x. This is the three-dimensional equivalent. We're taking the sum of infinitely many rectangular prisms, the volumes of these rectangular prisms, with a base of an area of dx multiplied by dt, and height f of x and t, or some function given by some function of x and t. So this overall sum is going to represent the volume enclosed between the three-dimensional surface defined by f of x and t, and the plane defined by g of x and t equals 0. Or just z equals 0, because the function's output is going to be in the z dimension. So you can notice this little drawing I've made up here shows the function defining a tilted plane, and so it's just a visualization showing what you're getting here using this integral, and here's finding the volume enclosed in this region between this function and this equals 0 plane. That's what that looks like. Alright, thanks for watching.